Hi everyone, are you able to hear me and see my screen clearly? Hi Abhinav, hi Balaji, hi Bintav, hi Kamal, hi Noor, hi Pawan, hi Pratik. All right, so all right, I believe that more people will be waking up and joining the class. Great. Before starting, there's a question from Bintav. I can read the slides in CloudxLab. Could we download them so that we can review them offline? Okay. Yes, definitely. We'll send you the PDF link, or we'll mention the PDF link in the CloudxLab itself, and you can download that. All right. So wonderful. So I'll do a quick recap of what we have done in say 5 minutes, and then we will continue from where we left. Okay. All right. So what we are doing is we are trying to do end-to-end machine learning project. And by the way of this project, we are exploring all the needed concepts as and when required during the project. All right. So this is an inverted approach. People do projects at the end of the courses, but I believe that this is the right way to do it. Okay. So we talked about setting up the environment. Then we talked about the checklist. We'll be following this checklist. Frame the problem, look at the big picture, get the data, explore the data to gain insights, and then prepare the data for machine learning algorithms. So this is where we are right now, exploring the data to gain insights. We are done with getting the data. All right. Okay, so here is the objective. Objective is to build a model of housing prices in California using the census data. This is how the data looks like. This is how the data looks like. We will talk about this data a while later. Question from Bintav is how to develop a machine learning algorithm that will come into play. And this is how you generally build an algorithm the way we are going ahead. Okay. All right. So, all right. There's another question that I need to answer. A question from Noor. Do we need a lot of statistics knowledge for this course? I did study this in school, but it's too long now. Do you recall to take a course in statistics in parallel to brush up the stats, or you will cover whatever is required? Okay, so we will cover whatever is required. Do not worry about statistics part. Okay, at any point of time, if you find a term confusing or not clear, please feel free to ask. Okay. Good, good. All right, moving ahead. So we downloaded the data, and then we downloaded the data, and then we started working on framing the problem to look at the big picture. So dataset has these kind of attributes: population, median income, etc. And every record was based on a longitude, latitude. Okay, let me just show you, I think. All right, so we got the data. This is how the records are. There is longitude, latitude, there is median age, there is total rooms, and so on. So for this district, these are the attributes. Okay, and this is the housing value. Objective is to build a model which can predict this given these details. Okay, given these parameters, our model should be able to predict this value. Okay, sure, Gigi. And those who want to record their own, I can give you the permission to record, so you can also record the session. Okay. Sorry. Okay. Feel free to ask for. I mean, I'll allow you to record. There is a button to allow you to record. Okay. Let me know if you want to record. Okay. That way you will get the access to the video like in an hour. All right. So we looked at the big picture, as in what is it that we are trying to achieve. Our model should learn from this data and be able to predict the housing price in any district. Okay, so again again we again asked and clarified that, are we looking to do it one time, or are we looking to build a model, and where will my model be used? And trust me, this framing the problem part is really hard part of the equation. And when you are given a challenge or you're given a project, what you need to do is you need to ask a lot of questions, a lot of questions. Okay, so you have to ask a lot of questions, and you'll realize that the whole strategy goes for a toss, as so if you decide on a strategy prematurely and then you take a look at the problem statement later uh, clearly and try to understand that, you will realize that most of the time we end up doing the entire engineering again. Okay, okay, so all right, so like here, what we need to do is we need to build a model which will fit in the data pipeline, and which will be converting the district data and converting based on the district data. It will be predicting the prices. Okay, and the census data is updated um, not so frequently, so we can build this model and deploy it such that it can predict prices. All right, so we also, while framing the problem, we talk to the current experts and try to understand how they're doing it right now. Okay, so, and we found out that the typical error was 15%, and the team basically gathers up-to-date information about the district. Experts use complex rules to come up with an estimate, and this is not cost effective and is very time consuming. All right, we also realized that the task was supervised learning and it was regression. Okay, and it is going to be most likely multivariate because there are multiple variables involved. Had it been only one or two attributes here, one attribute here, on the basis of which we had to predict the house value, then it could have been a single variable problem. Okay, all right. So Should we use batch learning or online learning? And we realized that we are going to use batch learning. Then we talked about the performance measure because we are going to predict the prices of various houses. So we would like to understand how much error is our model leading to. Is our model, the error should be a single number instead of a big array of numbers. Okay, so so that we can concretely compare the outcome of our approach. We can concretely compare the outcome of our approach. And this is a very important part in machine learning, that we do not leave this fuzzy. We always keep the performance measure of an algorithm to be precise and a singular number, so that we can concretely say that my algorithm has improved this much. Okay, and as a thumb rule, while optimizing anything, this is something you must do. That, let's say you're given a system or you have to predict some value, you always set down a performance measure. A question from Tanmay: how do you figure out linear regression or polynomial? Um, right now, that's exactly the challenge that we are going to solve going ahead. Okay, so we have not stated that it's going to be linear. Okay, we will use multiple techniques to do that. Okay, by plotting it, by doing other means. So we are going to do that while selecting the model. So there is uh, ta one of the tasks in the to-do list where we talk about selecting the model. All right. Okay. Now, here we took a little, we digressed a bit and we talked about statistical inference. We talked about variables. There is a correction here. There's a slight correction here. The continuous generally represents the decimal number. Okay, discretes are the kind of integers or fixed set of values where your variable can only say take certain set of values. Then we call it discrete. If the variable could take any value between the range, then we call it continuous. Okay, that is a slight uh, update there. Thanks to Kamal. Okay, a question from Tanmaya. These are all random variables. Not really. These are not random variables. They could be any attribute or variables, right? Like, for example, in our case, these are the variables. Okay. This is based on the survey. Is that your question? Tanmaya, is that your question? That these are the in this diagram? Okay, don't worry about that. We will go ahead. We were talking about the probability later. Okay, so in the beginning we talked about statistical inference. What is statistical inference? We will try to infer the behavior based on data using statistics. Okay, statistical inference is integral part of machine learning, because machine learning includes statistical way of solving problems, then algorithmic way of solving problems, and uh, and then much more advanced like neural networks and all. So basically the statistical inference is just one part of the machine learning. Okay, all right. So now, we talked about the variables. There could be various kinds of variables. Don't worry, even if you did not remember these definitions, because it's going to, it doesn't matter much. Okay. Now, okay. So Then we talked about random process. Random process is a process we know what outcomes could happen, okay, but we do not know which particular outcome will happen, okay. Then we talked about probability. Probability is the chances of something happening, and we generally calculate probability in order to take decisions, okay. In order to take decisions, we generally calculate probability. If probability of something happening is high or low, and accordingly we take the decisions. All right. So a question from Noor. In this slide, when we say that current error rate is 15%, what is the method of calculating that? Is there a method? Uh, is stats for that? Yes. Generally we use something called root mean square error, and that's kind of accepted way of computing error. But there are many more methods of computing error other than root mean square value. We'll talk about the various other methods, okay. And we will also learn that when to use which one, okay, when to use which one. A question from Tanmay is, can we represent the problem in vector form? Yes. Okay. So we'll talk about that part as well as we go ahead. Okay. So this is what you have suggested. This is true if we are thinking that the problem is a linear regression problem. Okay. When we can draw the line and do that. So we're going to study a bit more in this, and then we will come back to that. All right. Good points. Very good points. So we talked about probability. Probability is basically the chances of something, and we talked about the random outcome. And so in many cases, we must keep an eye open for the situation that the the outcome is still random, no matter what happened in past. Okay. Now we talked about what is the what are the chances of getting a total of 4 when we roll the dice. Okay. So what are the chances of getting total of 4 when we roll the dice? So what we did was we counted all possible outcomes that could happen, and then we also counted the instances when 4 as a total could happen, and then we divided the two numbers. Okay. So 3 by 36 is what we got. All right. Now, then we basically talked about if you start doing that for all the numbers, or not only 4, we start with 2, 3, 4, 5, and on the y-axis, if we draw the probabilities of that, it'll come like a bell-shaped. Okay. And this is generally called a probability distribution. Probability distribution is the distribution of chances for various values in your problem statement or sample space. Okay, so you can see that the extreme edge ends like 12 and 2, the probability of these is very low. Okay, the probability of getting 2 as the total is really low, because there's only one case in which you can get 2. Similarly, 12, you can only get 12 if both of the dice show 6 and 6, right? But in case of 7, there are many more ways in which you could get 7. 6 plus 7, 2 plus 5, 3 plus 4, and so on. Okay, so we also talked about at this point that most of the real life events have this kind of a graph. So say, for example, if you plot the graph of the marks in a class, let's say on x-axis you put marks in a class, and on y-axis you put the numbers, as in how many students got that marks, then you will find that that is also like that, meaning the average marks you will generally get in the middle. Okay, average marks will have the highest number of students. Very low marks will be for very small students. Very high marks will be for very small students, right? So this is generally the case. And sometimes we also try to figure out, is the data real or is the data fuzzy, by uh, uh, drawing it like this. We draw the normal distribution, and then we observe if this data was supposed to have a normal curve. So if somebody is let's say somebody a teacher did not conduct a test and declared the results that these are the marks of my class, then you can quickly draw the probability distribution and take a look at it. Compare the graph with the past year, and you can say that you have faked the numbers, or maybe you have given a very strange test, okay, in which everybody is passed or everybody failed. All right, so yeah, coming back to it, the distributions are skewed to the side of the long tail. So we talked about various kinds of skewness in the graph when we draw the probabilities, and the one which has long tail to the side, if it is the long tail is on the left hand side, we call it left skewed, because there are many values to the left hand side, right? If there are many values to the right hand side, we call it right skewed. And if both sides there are equal numbers, we call it symmetric. Okay, symmetric is something what we observe in most of the events in real life. Okay, so there could be scenarios where you have unimodal, as in there is only one peak. There could be two peaks. There could be there could not be any peak at all, or there could be multiple peaks. Okay, and here was a case where we talked about box plot. Box plot is a way of visualizing your data. Using box plot, you can quickly say that, okay, my 50% of the people are towards this side. My 50% of the population is towards this side, meaning the majority of our population here is having the life expectancy between 65 years to 77 years. This is what this diagram is saying. So it's very easy to visualize the data using box plot and see the probability, see the distribution of users very quickly. Okay, so this is how we okay, so then we try to show you that box plot and the curve and this is called histogram. Okay, is these are basically in place side by side. So histograms or probability distribution means the numbers of the probability is on the y-axis, and on x-axis we have the actual parameter. So histogram is generally plotted only for one variable. For one list of values, you can plot the histogram. Okay, it's like doing the plotting the word count here. Okay, and okay, same thing has been plotted like a box plot, and same thing has been plotted like a graph. Okay, now, then we talked about defining the center of data, and we learned that the median is the most stable way of measuring the central tendencies if your data is continuous. Okay. Now, the median is probably the best way of deciding the midpoint of your data. That's why for every district we are given the median house income, median house value, and median house age. Okay, so in statistics we prefer using median, Only in some cases we use mean. All right. There was one more question that we tried to answer yesterday regarding the mod. Okay. The mod is basically finding the mod is basically the most frequent observation. If there are two numbers having have if there are two numbers having the same number of observation, then we report both of them. Okay. If there are, like here, 88 and 88, there are two numbers which have the most frequent observation, then we are reporting only 88. Had there been one more 27, so we'll report both. We'll report 88 and 27, okay, instead of taking their average. All right. Then we talked about the robust statistics, meaning median is robust because if one of the data is suddenly skewed, as in instead of 6 there has been 1,000, mean will change but median will not. So the median is a stable way or robust way of reporting the central tendency or the central point of your data set. Okay, so here we talked about the same thing again. All right, then we okay, the other thing that we would like to understand about our data is how well our data is spreading, as in how is our data spread. Okay, so that's called variance. Variance says that how far is our data from the center point. Okay, so we define a center point of data and how the data is spread to the left and to the right, the overall from the center point. Okay, so the way we calculate the variance is very simple. What we do is we first calculate the median. Okay, we first calculate the median, then subtract that median from every value, and then square that, okay, and sum it. Let's say we had the life expectancy here, okay, of all the countries. We had life expectancy, as in for how many years do people live, the median life expectancy for each country. So if you want to see the how the data is spread, so what we like to do is we like to compute the variance. Okay, that's one of the measures of spread. So how do we do that? We will basically take a middle point by computing the median, and then or average. We also basically, in case of variance, we compute average. Okay, so we'll subtract that average from each of the value. Okay, that we will know that how far each value is from the center. Okay, then we square it and sum it, so that then we know that how far all of the values are from the center. Okay, and then we divide it by total numbers, and that's how we get the spread. All right. Question from Tanmoy. Question from Tanmoy is why n minus 1? Probably because this formula is not valid if the record is only 1. Okay, if the record is only 1, the formula is invalid. That's why we use n minus 1 probably. Okay. Or there is another way to look at it, why n minus 1, because there are total n minus total distances from each other is n minus 1, not n. If there are n numbers, total distances are going to be n minus 1. All right, so I think that's the reason, but I'm just taking a guess here. Kamal's question is, we could use median too here, right? As part of the variance, for whatever reason, we use the average probably. Okay, this is average. All right, as part of the formula, that's how they're doing it. But if I have to do it again, I would prefer to keep it median, not the average. Okay, so but as part of their definition of variance, they keep average. A question from Tanmay: Is it related to the ordinary least squares? Mm, no, I did not get ordinary least squares as in, are you talking about the root mean square value? Okay. Point from Noor. It is variance from center, distance from one point, and that point won't be into consideration. This is my understanding. That's right. That's right. Okay. So that's why I was saying that there could be total of basically, if there are n points, the distance between them would be n minus 1. Okay. So yeah. Thank you, Noor. I think that's a good point. Now, all right, now let's move on. So this is how we compute the variance. Okay, so okay, let me again talk about what does variance signify. The significance of variance is if the variance is high, that means the values are far away from the center. Okay, the variance is high, the values are far away from the center. If the variance is low, that means most of the values are around the center. Most of the values are around the center. And that's an important part. That's the way you interpret variance. If you see the variance to be too high, that means the values are far away from the center. Okay, variants are far away from the center. You will find more different kind of people or observations in this data set. Okay, if the values are, if the variance is small, if the variance is small, meaning most of the values are around the center, that means that you will not find too much of variation in the values in this data set, or that's how you can take a look at it. Okay. All right. Let me see. There are quite a few messages. All right. All right. So Binta's point is this is because it's of sample, not population, for more conservative. So safe is n minus 1. That's right. So there are two kinds of variance. One is based on the entire population, and other is based on the sample. Okay. So this is a variance of a sample, and I do not want to go into more details there. Okay. So this is good enough, and yes. All right. So okay, the next point is, all right, no worries. So I think we'll just stick with the formula for now. Okay. So Okay, a question from Pratik. For normal distribution, mean and median would be same. Okay, hence for variance, we could use both mean and median. So not really. Will basically stick with average with the variance if we are strictly following the statistical formula. Okay, and and we will also talk about few things here at later point of time. Okay, so all right. So the spread could be measured in many ways, and variance seems to be one of the ways. Okay, and that's the basically this is one of the ways of measuring the spread. All right. So here are a few questions that the other than n minus one or other than using why are we using average and not median. Okay, there are a few more questions that we would be having, that why are we squaring it? One of the reasons is that we want to get rid of negatives so that negatives and positives do not cancel each other. Variance is variance, whether it's a negative or positive. So that's why we are squaring it. But we could have done mod also, right? Mod as in, what is mod? Mod is basically if negative just multiplied with minus one or converted into positive. That also we could have done, but we want to emphasize the variance of individual more. The numbers that are bigger, the numbers that are far away from the center, we want to emphasize that one more. Okay, so so we increase the larger deviation. Square is, if you square 1, the outcome is 1. But if you square 2, the outcome is 4. But if you square 10, the outcome is 100. Okay. So as the numbers grow, the squares keep on growing further, right? So that's why we want to emphasize the deviation of individual value more than the more than we want to amplify the effect of big numbers more. So that's why we want to square it. Okay, so that's another way. And yeah, so and you will see this part as well in other formulas as well, that we will sum up the uh, squares of deltas. Okay, not only in the variance, but uh, in the say root mean square value, there also the formula will look very similar. Okay, so so the way we, if you take a look at this graph, here what we have plotted is on the x-axis it's a number, on the y-axis it is the square of it. Okay, so 2 square is 4, 3 square is 9, and so on, right? You can see that it's not a straight line. It's uh it's basically a rising curve. Okay, so for bigger values, the effect is more, the square value is far more. Okay, all right. So there are two questions which basically I'm not answering right now. One is why we have n minus one, not n. The answers from Bintao and Noor seem to be pretty valid. The answer is that since we are since we are finding finding the distance from a center point, so we are not counting the center point. Okay, this is one reason. And second is the second reason was that this is basically the population and sample one. This is basically variance of a sample, not a population. Okay, and there's a difference between the two, so that one I'm keeping it on a side right now, and because that will actually open up a lot of statistics here. Okay, so and and there's not too much required right now in our context. Okay, and the other question was why are we using average, not median? That also probably I'll have to look at it again. Why are we using the average, not median? Okay, so because the average is not stable while median is stable, or you can say robust. All right, so whenever we look at our data, we would like to take a look at the spread. Okay, and the spread is also measured in terms of the standard deviation. Okay, so so when we compute the square root of it, square root of variance, we get the standard deviation. We get the standard deviation. So if you take a look at this normal distribution, okay, let me go back a step. I think okay. So what we talked about is that we need to know about the center of the data, and we would like to know about how varying is our data. Okay, these are the two numbers we would like to look at. Also, the other these plots like histogram and the plotting the box plot, they give us a decent amount of information about our data, right? Now, the other thing is when we plotted the probability distribution of we throwing a dice and counting the total at uh, the total outcome, then we found that the graph was bell shaped. Okay, so that bell shaped is so common in the natural occurrences that I mean, people figured out that we could represent that as a formula that basically a formula which we can draw like a normal curve, like this bell-shaped curve. So based on a formula, we generally draw a graph. So this is the formula makes it a continuous instead of discrete, so that we can predict the outcome of predict the values for unknown numbers. Okay, so for n so okay, I think let me again explain. I think I'm skipping few points here. All right, so here, okay, so here we had two dice, right? We had two dices, and we could plot the graph by by throwing the dice and counting the probabilities, right? And we figured out that it is bell-shaped. But in many circumstances, in many occurrences, these values could be many more. The actual outcomes could be many more, such as a huge population, and we are counting the number of years they lived, and so on. So most of the people would be living for the average number of years, while there will be outliers on both the sides, right? So if we have a huge population and we would like to kind of predict the values for for any of the number here, instead of just instead of we trying to uh, find out somewhere between here, we could use a mathematical formula, because we can represent this as a mathematical formula which is very close to the real prediction. Okay, and this is called normal distribution. This is called normal distribution. So normal distribution, the curve could be drawn based on the mean and standard deviation. So if you are given the two numbers, mean and the standard deviation, you can draw this curve using the formula, and then you can predict that for this value, what is the probability or how many people are there for this value. For this value, how many people are there? So based on these two numbers, we can plot this graph, okay, and then predict the values. This is valid only if you know that your data is having the normal distribution, okay. All right. So when you draw this graph, you basically use two values. One is called average, the average value, and other is sigma. Or sigma is standard deviation. What is standard deviation? Standard deviation is square root of the variance. Okay, square root of this value. Okay, and all right. So so basically, the more the standard deviation, more spread will be the graph. The less the standard deviation, more steep will be the graph. Okay. So since the standard deviation is square root of the variance, therefore standard deviation signifies that how your values are spread uh, around the center. Okay, if standard deviation is small, that means your values are not too spread out. If standard deviation is bigger, you will see that the values are spread out. Okay, meaning there are many values. So here the center of the data is this, and there are many values away from the center. All right, so this is basically how the normal distribution looks like. Normal distribution is written as this equation. So here we feed in the mu and sigma, and we get as the x value, then here x value, mu and sigma, and we get the outcome. Okay, so this is called normal distribution. The area of this curve represents the whole population, and it is a probability on the y-axis. It could be either the actual counts or it could be the probability. If it's a probability, we basically say that the total of all the area of this curve is 1. Okay, the area of this curve is 1 in case of probability. In case we have drawn it in terms of the numbers, as in the actual counts, then the the area is area represents the total number of people. But in case of normal distribution, keep in mind that it is about the probability distribution. Okay, the bell-shaped curve is used generally for either probability or the total counts. Okay, so in this case, in case of this formula and the normal distribution, this is basically the total. The area of this curve is 1. The total, if you shade it and you somehow count the area, it is going to be 1. All right, so now what does it do? Why are we talking about normal distribution? Using normal distribution, we can predict the value, the probability of any of the values in this range. Okay, once we know that our values are matching the normal distribution, we can draw the normal distribution using the average and standard deviation and start predicting the values in between. Okay, so normal distribution is good for the case where our data is unimodal, meaning having one peak, and is symmetric. Okay, and is symmetric as in it is not skewed on either side. And if we have, it is good if we have continuous variables, not like throwing a dice. Throwing a dice is two discrete values, and therefore we can't really use this normal distribution there. It follows very strict guidelines about how variably the data are distributed around the mean. All right. Now, there are a few important facts to know about normal distribution that 68% of the whole data, 68% of the whole data is within one standard deviation away from the mean. Okay, so if we go to one value which is one standard deviation less than the mean, and to another value which is one standard deviation away from the mean, the overall values in this white area will be 60% of all of the data. And if we start at if we start at two standard deviation away from the mean and go up to two standard deviation above the mean, then most of the data, as in 95% of the data, is covered. Okay, so if you compute the standard deviation and you have a value, if that value is bigger than two standard deviation from the mean, as in it's here, that means that value is in 5% of all of the data, is a rare. Okay, and now further you can see that if we go three standard deviation away from the center, we'll see that 99.7, almost all of the data is within the three standard deviation. Okay, so you can see that beyond three standard deviation from the mean, almost there is no data. There is only like very small data, like 0.3% of the data is beyond three standard deviation. So you can see that almost all values are covered within three standard deviation away from the center. So standard deviation is basically a deviation from the mean. Okay, and this is how we generally calculate if our observation is outlier or not. So if we say that when we have a data set and we take a value in this data set and we plot the graph and say that this value is lying beyond two standard deviation, we generally call that outlier. Or beyond three standard deviation is definitely an outlier. Okay, so in an observation, like in case of our data, if when we plot the data and we realize that the particular values are far beyond three standard deviation, that means those are outliers. Okay, so that's one quick way of predicting things as outlier. All right. Now a question from Kamal: Can I plot a normal distribution curve for any data? So not always. So that this is what it is. So we can only plot normal distribution. Normal distribution is an estimate. Is basically kind of we are trying to fit in the curve for our data. Okay, so it is good only if you have one peak and the data is symmetric. It is not skewed. It doesn't have big tail in your in there. Okay, for it is for continuous variables. It is not for the cases where the values don't exist for decimal numbers. Okay, all right, good. So in the above cases, yes, it will be useful. Okay, in our project at hand, the computation normal distribution could help us. Okay, all right. Okay, I would like to understand this third question. But if somebody does a blunder, then can it be still done? Okay, I did not get this question. Yes, we can plot. Yes, we can. SciPy provides a way to calculate this formula and plotting these values. Also, you can write your own Python code to to plot this graph using NumPy or SciPy using Matplot. Okay, okay. Maybe you can frame the question and I can answer again. Um, can we plot a normal distribution? Yes. Maybe it'll be just a distribution, not normal. Yes. So you will, if you, not all distributions will fit in normal distribution. Okay. So there are chances of error and yeah. So it's basically an estimation. All right. Now going ahead. So now here's a question for all of you. Okay. So a college admissions officer wants to determine which of the two applicants scored better on their standardized tests with respect to other test takers. Okay. So there are two persons, Pam and Jim. Pam earned 1800 on her SAT and Jim scored 24 on his ACT. Okay, so there are two separate exams. One person attended SAT, other person attended ACT. Okay, they both sound same. Okay, and the scores are basically like this. One got 1800, other got 24. Now here is a little bit more information about it. The more information is that one, it's a normal curve, it's a normal distribution. Second, the mean of the data is 1500, mean of SAT scores is 1500, and standard deviation is 300, while in case of ACT scores, the mean is 21, standard deviation is 5. Now question is, which candidate out of these two, is good? Yes? Who is away from standard deviation? Who is let me put it again. Who is more standard deviations away from the center? So Pam is 1800, right? So how far is Pam from the mean? 300, right? That means one standard deviation, right? And I think this chart shows you better answer. So you can see that Pam is one standard deviation away, right? While Jim is zero point 0.6 standard deviation away. So what we did was, first we found out how far is Pam from the center, right? And from the mean. So 300, right? 300, and then we divide by standard deviation just to compare how far is Pam, how many standard deviation is Pam away from the center. Okay. Similarly, for Jim, we subtracted 24, we subtracted 21 from 24 and divide by 5. So you can see that Jim is zero point 0.6 times standard deviation away from the center, while Pam is one standard deviation away. Now, who is outstanding? Actually, Pam has done better. Why? Because if you see, Towards the left are lesser marks. Towards the right are higher marks. Okay. So PAM is towards the higher marks. Okay, because PAM is better than PAM is more standard deviations away from the center than GEM. All right, so it's an important question to answer. Given two separate exams, given two separate tests, we were able to still compare the apples and oranges, right? Generally, we don't want to compare apples and oranges, right? And that's how we look at the data and try to estimate. All right. So next time, if your kid or your cousin comes from school and tells the marks, you must ask about the mean and the standard deviation. Okay. You must ask for mean and the standard deviation. Only then you'll be able to tell that how well is he doing. Is he outstanding or not? Okay. All right. So, okay. Yeah, I should ask my kid also next time. All right, good, good. So a question from Tanmay is, what if it is multimodal? Okay, what is if it is multimodal? Multimodal means if there are two peaks. Good question. So what if there are two peaks? Okay, and in that case, the rules, the one which we learned here, would not apply. Okay, because there are two peaks, and and basically if you have two peaks, then the mean and the meaning of the whole curve goes for the toss. In that case, you will have to maybe ask for the actual data. Okay, unimodel is the assumption, and it's a good assumption because unimodel and the normal distribution is actually looks like a big assumption, right? It looks like a big assumption because we are basically extrapolating that our data fits the curve. But good news is that it does fit a lot of real life scenarios. Okay, very good question. All right, moving ahead. So we're going back to our problem. So this is pretty much basics of statistics that we covered. If needed, we will deviate again and we'll learn those parts from statistics. Okay. So I hope that things are okay for now. It doesn't look too complex. All right. Abhinav, Balaji, Bintao, Giji, Kamal, Noor, Pavan, Pratik, Ross, Shahrukh, and Tanmay. Things are okay, right? Right. Based on your feedback, I will try to either slow down or base up. Okay. It's good that we are only a small set of team, so we can actually improvise as we go ahead. All right. Okay. So there's a Kamal's question. Let me just clarify that one. I think it's good to clear that because that question would be there with everybody else also. Question is, I still have one confusion that maybe I might just assume and force fit a data to normal distribution. Good, good. So, and that's a valid point. So in a lot of real life scenarios, we realize that we have a couple of options. One is we draw the actual graph and try to try to compute the standard deviation, variance, and so on, and then use these terms like uh, use the normal distribution and predict the values, right? But this is not true in many cases. We can't really use normal distribution to predict all the values, right? Because the real data may not be like normal distribution always. Okay, but normal distribution is a good estimation for many problems. Okay, specifically if you have the continuous range of data and you have unimodal and you have symmetric. So in that cases, it can be used. But as Dhanma is suggesting that what if curves are skewed, then you can't use normal distribution. All right. It's only for the cases where it's not skewed and it's symmetric. All right. But normal distribution comes as very handy tool to predict many values if we are sure that the data is roughly fitting into this kind of a curve. Good. All right. So now we were talking about framing the problem. We were talking about the framing the problem. Okay. And so we were talking about computing the error as in the the root mean square value. So one of the things that we must do is figure out our performance measure. And here we are talking about root mean square error. Let's say we want to predict house value based on house area in square feet. We will use a single variable, univariate linear regression. Just okay, we'll describe more about what is linear regression soon. Okay, so we will use kind of univariate linear regression, meaning we are assuming that the data is fitting a single line, a straight line, right? The way we do with the pen and paper, that this is my data and this is my line. So that's a linear regression where we try to fit the data and approximate the data based on a single line, right? Univariate means that our data is only varying based on one variable. So we are saying that let's say we were trying to predict house value based on the area, only area, not any other parameters. That means that there is only one variable. So we call that univariate since there is only one feature. All right, so this is how the linear regression looks like. So if we plot house value on y-axis and house area on x-axis, let's say the data points that we got was this. Okay, data points that we got was this. So what we'll do is we will try to fit a line. Now that there could be many lines, right? There could be lines with a different slope, the line that could be a little above, line that could be a little below, and so on. There could be many lines that could fit these many data points, right? Because they are not in the single straight line. So we need to approximate, and we are saying that this data may be looking like our linear regression, okay, meaning they might fit a single line. Okay, there is, so what we do is we realize that we have drawn the line, but it may not be the best line possible. There would be an error from the actual data. So what we do is for every value in the data point, we compute the predicted value. Since this is our line, this is hypothesis. This is the hypothesis. So it's basically the 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 predicted value of y, which is away from the actual. And how much away? This much away, right? Similarly, the other second data point is this much away from the actual. This one is this much away, and so on. So we want to minimize this error by changing or shifting the line up and down, changing the slope of the line, and so on. So But before doing sifting of the line, we would like to keep our measure, performance measure, clear. Okay, and that performance measure is the error in the prediction. We want to minimize the error in the prediction. How we do that? First, we compute the delta. For every point in this data set, we predict the y value using our line. We subtract that from the actual value, and similarly we do that for all the points. Then we square it again. Why are we squaring it? So that the negatives becomes positives, because when we square something it becomes positive. And also we want to amplify, we want to emphasize the greater error more. Okay, and then we sum up all these errors in every point, and then we divide by total number of points. So we sum up this, this. Okay, so this is how far these data points are from the actual values. Okay, sorry, this is how far our line is from the actual values. Okay, so and then once we are done with that, we divide all of this by total number of points, and then we compute the square root of the total. Okay, that way we get the error. Now we have to minimize this. That's right. Now we have to minimize this. So algorithm might try to fit many lines into the data. We would keep on increasing the slope or decreasing the slope, or we will keep on shifting the line up and down. And how do we do that? By changing the slope and c. Okay, so basically the house value as per this line, the actual house value is W naught, okay, and plus W1 into house area. So W1, let's say that W1 is the slope. So the house value is some multiplication of house area, added by some other value. So these two things is what we need to identify. The algorithm has to figure out the best values for W naught and W0. Oh, sorry. Okay. Now, what is wrong in this? So based on the house area, we are trying to predict the house value, right? Okay. All right. No, I did not get Abhinav. Could you be specific? So, okay. So we are trying to basically figure out the house value and based on the house area. Okay. So we are saying house value is some multiple of house area added by some fixed. Okay. So, all right. So basically, this is a kind of a rough picture of what we are doing in case of, say, linear regression. We're going to explore more into this using our further approach. Okay, so we just wanted to describe what it means by linear regression. And yes, this is where a question from Tanmay, this is where the gradient descent comes into picture, because what would happen is if you start trying all possibilities, right? there could be, say, if there are 100 possibilities for W0 and there are 100 possibilities of W1, so total number of possibilities are how much? 100 into 100, right? For each value of W0, we'll have to try every value of W1. If there are total values that we would like to try for W0 are 1000, and the total values that we would like to try for W1 is 1000, so there will be a million combination, and therefore it's going to be very time consuming even for just plotting this line, right? This is where the optimizations come into play. Instead of trying uh, all possibilities, we try only those lines which are basically closer to which are basically leading to the better results. Okay, so if we drew a line, if we changed W naught and we found that it's going bad, then we basically change the W naught in other direction and observe. So we try to go in the direction which is yielding better results instead of trying all possibilities. Okay, that is what we call gradient descent, and we'll talk about gradient descent in more details later. Okay, so a question from Noor is that could you describe W naught again? So basically, this formula could have been valid if this line was passing through the center, if there was no W naught. Okay, if we said house value is a function of house area, house value is a function of house area, okay, and there was no W naught. So had it been W1 into house area, this line will be coming from center, right? So let me draw this. I think this will make more sense to you if I draw it here. Okay, so imagine that you had this, you have these data points, right? And so you will try all possible lines, right? Like this. So this could be one line, and you would like to try different lines, but all passing through center. Okay, all passing through center, and so on, right? But there could be, with the same slope, there could be many lines here, 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 here. Okay. Okay. So when we are basically not changing the slope of the line, we are basically varying W naught. Okay. This is how we are varying W naught. If we are changing the slope, we're changing the slope and keeping letting it pass through the same point on this axis, we are only changing the W1. Okay, that is the slope. Okay, so this is the slope and this is the intercept, as in how much, where is it cutting the y-axis. That's the W naught. Okay, so we are basically varying the two parts. Yeah, we may call the W naught as base house price. W naught is the house price in case the area is 0. Okay, in case the area is 0, then house value is W naught. All right. So did it make sense to you, Noor, the manual approach? We do change W naught. So we'll basically have to change both. We'll have to keep changing this is how we are changing. When we are lifting this line up, we're basically changing W naught. Okay, we are changing the W naught. But if we are just changing the slope and not changing its position here, then then we are only changing the W1. Okay. So let me just, instead of rotating it, if I draw many lines from here, so this is one line with same W naught. This is another line with same W naught. This is another line of, this is not a line. Okay, this is another line of same W naught. Okay, so we're just varying the slope. That's right. There could be many more variables. There could be many more variables that are impacting house value, not only house area. There could be many more variables, and therefore the problem becomes complex. Okay, we'll be drawing house value as a function of those variables as well, and then it'll become complex. Okay. Okay, so how do we know which that particular line fits best? By minimizing this error. The line that has the smallest root mean square value will be fitting the best. The hypothesis from Bintao is that the most one could be the location. Most one could be the location. And it's just a hypothesis, and this is something which we are going to explore further. Okay, so let's keep a hypothesis, but let let's be open to experimentation. Okay, so we got the data last time when we talked about, we basically um, downloaded the data, right? The data was already there in our GitHub repository, but this is a public data set. You can also download it. So what we have is we defined a function. We defined a function to load the data, and then we read it. Okay. So this is the data, so which we have already. I hope everybody is able to see this. Are you able to execute this? Did you execute by running shift enter? Okay. So there are 10 attributes. So what you see here is there are 10 attributes: longitude, latitude, median age, house as in how old is the house, then the total rooms, total bedrooms, and population, household, median income, and median house value, and then ocean proximity. Okay. Now, the info method is quite useful. We could simply say house.info, and it'll give us a quick, it'll give us what's with this? Okay. So here, the info method is useful to get a quick description of the data. So let's take a look at what is it shows. It shows that it shows the information about all the columns, right? It tells us that there are these many records, except here the total bedroom information has only these many records. Okay, so total bedrooms are missing for 207 districts in this, and all attributes are numerical except for ocean proximity. And its type is object, so it could hold any kind of Python object. But since we loaded data from CSV, we know that it must be a text attribute. Okay. All right. So Or also we can just take a look at more number of records by saying housing simply, and there are quite a few records there. So this way you could take a look at the data set. No worries. Now, all right, I think that's pretty much. All right. Now, in case of every variable, we could always why it keeps on. Let me just reload it. Okay. Now, so we took a look at the data set this way. There are quite a few functions which could be useful. So to understand what kind of values are there in ocean proximity, we can do the value counts. So here it shows that these are the various values, right? These are the various values in this column, right? Inland, near ocean, near bay, and the ocean. Basically, these are the various value counts, that these many houses are at the ocean, and these many houses are nearby, or these many data points, I would say these many data points are nearby, and so on. Okay, so the value counts gives you a quick word count. All right, then we can describe the housing. The describe function gives you a far more useful information about the data. Okay, so when we do describe, we get the summary of all the numerical attributes. Okay, so what we get is, here we get the total counts, okay, then mean, then standard deviation, the minimum, and we get the percentile, right? You remember we talked about percentile while we were talking about interquartile range. So you can see that the 50% of the data is basically from this to this. Okay, 25% of the data is below this. Okay, while 75% of the data is below this, and the max is this. Okay, there is, yeah, max as in, because it's a negative number, so max means the smallest negative number. Okay, so you can see that 75% of the data is below this, 50% of the data is below this, and so on. And here the standard deviation is showing that how the values are spread. Okay, the bigger the standard deviation, more is the value. So you can see that in case of a median, the standard deviation is 12, and in case of total rooms, the standard deviation is further more, and so on. So again, 25% is called first quartile, meaning 25% of the districts have median age of lower than 18. Okay, 25% of the houses have median age lesser than 18. Okay, 50% of the houses have the median age less than or equal to 29. 70% of the houses are lesser than or equal to 37. Okay, Question from Bintao is object a data type in Python? Yes. Whenever we define our class or class and then there is an object of that one is called object in Python. Okay, great. So I hope this is clear to you. What does it mean by 25, 75% and so on? Yes, 25% is same as the first, not really, it's not first deviation. It's basically the one which when we talked about the the one which we talked about in let me show you. Okay, so this is the one. Okay, so up to here this 25% data, up to here the 50% of the data, and sorry, 75% of the data, and remaining is 25% of data. Okay, that's what we talked about. And the okay, here, right, this one, correct? So first standard deviation is actually 68%. Up to here it's how much is 100 minus this by 2, that percent. Okay, so it's not first standard deviation. Okay, Noor? All right, good. Now, now let's plot the diagram. I think this will be better. Okay, now let's plot the diagram in the form of histogram, and to get the feel of how the data looks like, what kind of data we are dealing with. We can plot histogram only for numerical values. And so this is how we plot. So we are basically saying matplot inline, okay? And then we are saying import PLT. We are importing this module as PLT, okay? And then we are saying housing.hist. It's going to plot the histogram of every variable separately. Every numerical variable separately, it's going to plot. Okay, how many variables are there? There are total nine variables, which 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, the 9 variables are for that, and 10th variable is the categorical variable. So categorical variable we are not plotting here. Okay, all right. So what you're going to plot is for each value, each numerical value, it's going to plot the frequency. So on x-axis, there is value of households, and on the y-axis, it's the count of records which have that many household. Okay, so on the y-axis in histogram, it's the count. Okay, what's the figure size? Figure size is essentially the size of each diagram. Okay, all right, I'm not sure if it is in pixels. Now, what you see here is something really interesting. So household looks okay. It looks like a normalized curve, just that it is right is skewed. There is so much data on the right hand side. While in case of median age, right, this data looks like it has two ranges, or there it has kind of two peaks. But there is a strange peak on the extreme right side. Looks like the whole data has been just put at one point. Okay. And in case of latitude, we have a similar two peaks kind of model. And yes, so we okay. So what does it mean, the matplot inline? Matplot inline is basically to use the matplot inside Jupyter notebooks. It becomes easier to do this way. Okay. All right. Next, so you can see this. All right. So what did we observe? Okay. So what did we observe? We observed few things. I think this is better. Okay. What we observed is that a lot of data is towards this side. Okay. In case of median income, there are these outliers here. There are some outliers. There's a long tail to this side. Okay. So that's the first observation. Second observation is that the data is capped as in looks like all the values bigger than this have been brought to this value. All the values bigger than 50 have been set as 50. That's what we observe here. Okay. So the median income attribute does not look like it is expressed in USD. Okay. It doesn't look like because this is some other. Okay. After checking with the team that the data collected, you're told that the data has been scaled and capped at 15. Okay. The data has been capped at 15. Okay. And so, okay, let me explain. So you see that here also, even in the median income, everything was very small, and suddenly there are quite a few users at close to 15. Okay, at close to 15. Why? Because all the values which are there above 15, they have been kept at 15. Okay. All right. Now, again, the same thing. So house value and median age also are kept. Okay. So because you can see that this is really strange. In the real data, it would never happen that on the final value, suddenly there are so many records. On the max value, there are so many records. The only reason for this is data is manually set, as in somebody has basically fitted all the values beyond a certain value as that value. So here all of the values above 50 have been set as 50, and here all the values above 50,000 has been set as 50,000. Now this is a serious problem. So we checked with the team if this problem is not i- is true or not. The team says that they need precise predictions even beyond 500,000. Then okay. Okay, so what does it mean? Let me go back here. I think that this will describe better. So here the data has been capped. So here, in case the team needs better predictions even beyond this value, then we will not be able to do that. We'll not be able to predict based on more value than this because we don't have data beyond this. Okay, so so if as per the real use case, if the team needs the predictions even beyond the max, the value at which we have capped it, then we'll have to collect proper labels for the districts whose labels were capped. remove these labels from the training set as well as the test data set. Okay, we could do either of the two. We'll completely delete this particular data set and then let it extrapolate. Okay, so I think it's break time. I again missed it. So let's take a break. 10 minutes. We are at 8:40. We'll be back by 8:50. Back by 8:51 a.m. IST. All right, so I'm back. Should we start now? All right, so let's start. All right, great. So let's start. All right. So what we learned before the break about, okay, let me go back. There are a few questions about it. Okay, so percentage matplotlib is a Jupyter specific syntax whereby we are saying that plot the graphs in line. Okay, and let me describe this syntax. So we are importing this pyplot as PLT. Okay, and then we are saying that we plot histogram of all of the variables on this plot, and then we show the plot. So first we plot it using histogram and then we show it. Okay, this is what's happening here. While plotting the histogram is nothing but frequencies of data within certain range. Okay, histogram is that how many values are between 0 to 10, so that's one bin we call it, and then how many values are there between 10 to 20, 20 to 30, and so on. So what we do is we take the data, we take the range of the data, the bin, we call it bin size, and we say that how many values are there in this bucket. Okay, so if we talk about say latitude, or let's say median age, what it will do is it will, let me go up. Let's say we are trying to compute the histogram of based on the say total bedrooms, right? Total bedrooms. So what will happen is here, here it will basically break it down into buckets from 200 to 300, 100 to 200, and 300 to 400, and so on. So basically it will count the, it will first create the buckets of some size and then count the numbers in bucket. Here we are saying the bucket size for all is not, no, it's not bucket size, it's the total number of bins we are saying as 50. Okay, so total number of buckets we are saying to be 50. I think that's what it means. Okay. All right. So if you want to take a help documentation of say the hist function, you will get an idea. Okay, so it has bins, the number of histograms bins to be used. Okay, total number of buckets. All right, so I hope that's clear. All right, does it make sense to you? Okay, so if you do not use matplot inline in your code, it will not display the image. Okay, basically it's telling the IPython or Jupyter to plot things here. All right, because instead of trying to figure out the graphics port and all that, it's plotting the graphs on the web interface. All right, good. Next thing to notice is the in case of say these two variables, the population and where is the population? You can see that population and total bedrooms and total rooms. You see that? What do you see here? What do you see here? Anybody? In case of total rooms or total bedrooms or population, what is your observation? Quickly. No observation. So yes, there is a skewness in the plot, meaning there's a big tail on the right hand side. You see here the tail is going till this point. Okay, so there are tail heavy histograms. Many histograms have heavy tails. This is harder for machine learning algorithms to detect patterns. We will transform these tails into a proper bell-shaped distribution. We will do a little bit of data churning in order to convert, I mean, remove these tails and push it to this side. Okay, we'll learn that part. Okay, so this is the phase where we are preparing our data and trying to understand what could be done in order to fix the data. All right, now basically the next important thing, this was very rough overview of our data. We took a glance at various histograms of all the fields. So now is the time that we create the test data set. Okay, what is test data set? Test data set is basically used for testing. Okay, now what we do is we take our whole data set, we break down the whole data set into two parts, training and test. Training usually is 80% of the whole and 20% of the remaining is test data set. So these records, you see these records above in the basically the housing ones. So what we have to do is we will have to predict the prices, right? For that we'll need to prepare a model, and to prepare a model, basically we'll have to measure our model continuously to understand how well are we doing. But how will we measure it? Okay, how will we measure the predictions? Okay, we will measure the predictions based on the historical data, right? If a fortune teller comes to you and tells you that he can tell the future, then you ask him about the past, right? And that's what we are going to do with our algorithms, right? That's what we're going to do with our algorithms. Certain amount of data, we'll keep it as separate called test data. And whatever algorithm we come up with, we will run that algorithm on the test. Once we have come up with the model and the algorithm, we'll run that on the test data and see how well are we doing. We can compare the different approaches with each other by comparing the results on the test data by the way of counting the error using root mean square values of error. Okay. A question from Bintao: how do we know when I do need to import which binary, such as NumPy, pandas here? So basically, I would say that you always keep these two things imported. One is NumPy, okay? Other is import pandas PD, okay? That's the thing. So in whatever project you start, you should import these two libraries upfront, okay? All right, so let me repeat again. So what we talked about is that we generally split our data into two parts, training and test, so that whatever algorithm we are coming up with, we we come up with our algorithm based on training set, and we test our data on the test set. Okay, we come up with algorithm using training set, and we check that model. We come up with our machine learning model using training set and test using test set. Whatever is the, we basically run our model on test set and predict the values, and then compare the root mean square of the error, okay, between various models. So test set is going to be used here, okay? So this was the first question probably somebody would ask me. I think I asked that question first, that yeah, I can build a prediction, but how am I going to make sure that my predictions are good? I'm going to predict the house price is fine, but how would I know that they are doing good? So you basically pick some of the existing data, remove the pricing part of it, and then you predict the values and compare with the actual one. Okay. All right. So we train the model on training data and evaluate the performance of the model on test data. Okay. Test set or test data, I'm going to use the two words interchangeably. Okay. All right. So why do we need to create test set right now? Okay. Generally, we should create the test set right in the beginning. Why? Because there is something called data snooping biases. Okay, so we are pretty clever in that sense. We are pretty clever in the sense, and almost in any work, the chances of telling the pattern based on the outcome is very common. So we are basically going to snoop at the result and trying to fit our model into the test somehow. Okay, so if we know, let's say if we are competing in a competition, and if we know how the system is going to check our result with, then we will basically optimize our model for just the outcome, and that way we end up building a bad model. Okay, so we should, in the beginning itself, we should basically pick up the certain test data set and keep it away. Should not take a look at it, take a look at the values, and our model will be too optimistic with respect to the data we are comparing with. All right, so keep that in mind. So in this project, we are going to use scikit-learn's train test split function to create test set. And we are also going to learn in a couple of slides that how to create our own split function. Okay, it's important because you will see that why are we trying to create our own split function, so that you will learn in a couple of slides. All right, so let's take a look at it. So what we're going to do is we're going to create our own function to split the data. All right. We're going to create our own function to split the data. So first of all, what we are going to do is we are going to set a seed for random number. Okay. So in case of NumPy, we used something called random, and random numbers in computers are always kind of pseudo random numbers. There is a seed. Based on the seed, the random number is generated. If the seed is same, the random number will always be the same. Okay. Seed is generally time, and that's why the random numbers always look different. Okay. So mostly the random numbers are mostly predictable. If me and you both set the same seed, we will both get the same random number. Okay. And if the seed is say milliseconds or some other common number, like me and you press the enter at the same time while the seed was the current time, the chances of both of us getting a random number is really high. Okay, so seed is basically the basis on which the random number is generated. Okay, all right. So that's why we first define the seed here. We're saying 42. You can keep 10 or whatever, but we're keeping it fixed. Okay, and I'll explain to you why are we doing this fixed. Then we import NumPy. Then we define our own split test train test function. Okay, it takes the input data set, and it takes a ratio, and it returns the splitted data. Okay, and here is doing very simple thing. It's first generating the np dot random permutation. Okay, what does np dot random permutation do? I'm going to show you that part. Okay, so let me show you what it means by np dot. So np dot random permutation. Okay, I'll do it here. Okay, so np dot random permutation, it takes a number as argument and prepares a permutation This permutation is basically from 0 to 9. 0 to 9, it has produced a certain combination. If we execute this again, we will get a different arrangement of numbers. Okay, so every time we run it, we'll get different numbers. Unless we are also calling the seed. Unless we are also calling the seed. Now the number will always be the same. Now the number will always be the same. Okay, so random permutation generates a random permutation of numbers up to certain value, up to a certain value. Is it clear? What does random permutation do? Then, okay, before proceeding further, there is a good question from Bintao. How do we know when I have to create our own function, right? So generally we don't have to, but um, this is kind of important to have the understanding of what's going on. Therefore, we are going to learn how to create our own split function. Okay. And there are some very important things that we're going to learn as part of this. Okay. So this permutation is going to generate all of the indexes, right? Because it is starting from 0 going up to but not equal to that number that we have passed. So it's going to generate it's going to generate an array of numbers from 0 till the length of data. Okay, till the length of data. Okay, once we have done that, we'll have the shuffled indexes. These are the indexes of the data, not the actual data. These are just array of numbers from 0 till the length of data. Now, the size of the set is basically the length of data multiplied by the ratio that we have passed. So the ratio that we are going to pass here is the how much percentage of the total data needs to be in the test. Okay, so this is going to be 0.2, right? That's what we have discussed. It's going to be 0.2. So we figure out what is the size of test data set. Okay, so it will be basically um, total length multiplied by test ratio. Okay, so test indices are, we are going to pick some of these indices, random generated indices, okay, for test indices and some of these indices into train indexes. Okay, so from say 0 till this size, we are creating two sets of indexes. Okay, so we are slicing the shuffled indexes into two parts. One is test, other is train. Okay, once we have done that, now we can use iloc method on the data frame. Okay, on the data frame to extract only those values existing on those indexes. Okay, what is iloc? Remember, in case of pandas, we discussed how to access the rows, not the columns. Rows based on index, right? So it's if we talked about housing, right? Housing, and we say iloc 0, right? So we get the first row. This is first row. If we say up to 5, we will get first 5 records. Okay, remember that? So that's what is happening right now. Also here we could pass an array of some random numbers and extract those row numbers. See that? iloc gives us records based on the row numbers. So that's what we are doing. We created these random numbers for training and test, and using that, we are extracting parts of the data set. And we are returning a tuple. Here, when we are saying A comma B, we are essentially returning a tuple. Is the function clear to all? No? A question from Noor is, this seems to be a common approach to create a data set. How is it different from built-in function? We will talk about that. Okay. So first, let's try to understand how does it work. Everyone, are you with me so far? Does it look too much of code? So first we generated a random set of numbers from 0 to the length like this. Then we cut it into parts. This went into test. This went into the training set. And then we used these two lists to extract the actual data. This is where we are extracting the actual data. So we broke down a huge data set into two parts, one for testing, other for training. On the training, our model will be built. On the testing, our model will be tested. Okay. On the test data set, we will be testing our model. Okay. So let me just define it first. Okay, also there is a minor correction in this one. We'll have to define the random seed here so that the permutation is same every time. Okay, every time we make a call to this function, the permutation we get is same. Why are we doing that? If we do not keep a random permutation, what will happen is, sorry, if we do not fix the random permutation, what will happen is every time our model will run, it will be trained on different data set and will be tested again different data set. And the chances are that we will end up snooping over whole of the data. Our model will end up looking at the whole data eventually. Therefore, it's important to keep the test data separate from the training data. Okay, question from Noor. So if input seed is constant, it will generate set even if we restart the process. Yes. If even if uh, so for you also you will get the same result if you run these two commands. Okay, if you run these two commands, you will actually get the same result as me. So for all, this will basically makes it unrandom. All right, so this way we have been able to create a function. Yeah, this is good enough to say this is the right way to do that because we are making a call to this one only once. Okay, why I am putting a seed here? Because if we call this function twice, okay, then this seed will be removed for next time. I'll show you. So if you see this, I'm saying print this, right? So what should be the outcome? Should it be same both the times? Yes or no? It's not. Okay, it's not. Why? Because the seed is used up here and it again goes to the random seed. Okay, all right. So that's why if you set up the seed, you can see that both the values are same. If you remove this, then both the values will be different. Okay, you can see that every time the values are changing. Good. That's why I would like to set the seed here. Default seed, I think, is based on time. Default seed is, I think, based on time in the nanoseconds. Now, we can use this function that we just defined to split our housing data such that we get test data set as 20%. So we are saying train comma test equals split this. Okay, and here we get the results. So it is showing us the length of both of the data sets. Length of both of the data sets. So it has created two data sets, train underscore set and test underscore set. All right. Okay. So we would like to keep our data records fixed. This is a very important thing to know that the otherwise we would, if we do not keep the permutation or the text, this selection of test and training data set same, what will happen is on every run of this function, training data and test data will be different. And over time, our machine learning model may end up seeing the whole data set during the training, which we should avoid. If on every run we're making call to split multiple times, and on every run we are seeing the different data and different data in the training set, so we end up seeing the entire data in entire test data as part of machine learning preparation, machine learning models preparation. And that would mean that we are looking at the output before working on the input, right? Before working on the training data, we're basically try looking at the output all the time, okay? Um, Looking at the test function. Question from Tanmay. In this function, we sent dataset copy. We did not split, as in we did not slice the actual data. Basically, after splitting, one part we sent to one part. This when we say here, when we say iLock, we did not change the existing data. We basically produced a new copy of the records. Okay. Okay, this we have discussed already. So for random number generation, we are explicitly specifying seed in order to keep the same data set. Okay, and now here is, this one is working fine, as in when we split the data, we get these records. Okay, now what is the problem with this function? What is the problem with this function? Do you think there would be still the cases where it will give us different values for test and training? Will there be any case where it will give us different records in test and training? Yes, no? So we created a split train test function, which breaks down our actual data into two parts. So do you think there's a problem with this function? This function is, all it's doing is it's generating the random sequence of indexes and extracting values or copying values from the existing data set into two separate data sets. Okay. A suggestion from Tanmay is that we might have to check the test ratio also. So the way we checked the ratio was here. We basically multiplied the length with this, and using that we extracted data. Okay. Yes. A question from Noor is, I think the best approach is to have more samples from one standard deviation than other deviation. Here it's uniform. Okay. Uh, interesting question. Interesting question. And I think I'll answer this question. This is an interesting, very relevant question. I'll answer this. I'll discuss this part when we talk about stratified sampling. Okay. Stratified sampling. Okay. So the problem with the problem with this function is, what would happen if we add more records to this data set, right? If we add more records, say even one record, if we add to the data set, the entire data set will change. Why? Because all the indexes will move, and even though indexes are fixed as part of our program, the actual values will shift, right? if we update the record or insert a new record in this data set, then the entire data sets, both the testing and training, both will change, correct? Because row numbers will change. Right now we are accessing things based on row numbers. Still it will be 80-20, that's right. Still it will be 80-20, but the values of both the training dataset and test dataset will change, right? If each instance in the dataset had a unique immutable identifier, meaning right now we were trying to access the records based on the row number, and row number changes if we insert even a single record, right? And hence the entire data set, the model becomes completely different, right? Therefore, what if we could identify each record with something, and then based on that identifier, we we pick up the record, okay? So that no matter what happens, we always have the same set of records. No matter what happens, we always have the same set of records in both. So we need to decide a basis of identifier, okay? So and based on the identifier, the way we compute is we compute the hash of each identifier, take only last byte of hash, and if last byte is lower or equal to 51, we pick it, okay? So I'll show you this one. I'll explain you in more detail, okay? Okay, let me show you here. Okay, all right. So this is how it looks like. Okay, let me go down a bit. So let me first describe to you this function. So here we are creating a completely new function called split train test by a certain ID. Okay, good point from Kamal. Kamal's point is we might as well just persist the test data and train data separately and append new data proportionally to each. Okay, okay. So here we are going with batch learning. In batch learning, you will get the whole data set again. Okay. And therefore, first you'll have to figure out what are those new records and then add those new records. Right? And that could be a very big approach. That could take a long time. All right. So there are some things here, and I think this is important to learn. And okay. So here I'm going to, describe something important. Okay. I'm going to describe something important. Before moving further, I'll actually describe what is hash. Okay. I was trying to avoid it, but it seems that we will have to know these parts. Okay. Because the fact that we have cryptocurrency around, we have so many other things around. So it's important to learn the part of hash. Okay. Now, all right. So in computing, we often need signature, whether it's a big image. This is some image, okay, this is some image, or whether it's it's a big text file, some text file, or some music, right? So we want to identify them with a signature. Okay, signature should be such that that we can create signature from here to here. Okay, we can create signature from image to uh, we can create signature from image, signature from text file, or signature from music. This should be possible. Okay, this should be possible, and signature should be signature one. Okay, and it should be such that signature 2. Okay, let me just signature 3. Okay, it's a very important part, and this is something which we all must know when we deal with computing. Okay, I'm sure most of you would be knowing it already. So we often need to do signatures of a huge data. The quality of the signature is all of these are fixed size. These are fixed size. Okay, no matter whether it's 100 gigabyte data, or it's 3 MB data, or it's 100 KB data, the signature will always be of the fixed size. It will be, say, 64 bits. Okay, fixed size, it could be 64 bits, 64 bytes, okay, or 256 bytes, and so on, right? Either of these. So we often need to create signature, and that's what is, there are many algorithms to create signature. The other property of signature is nobody should be able to uh, create the actual content from the signature. Okay, nobody should be able to create this. Okay, from the signature, we should never be able to create the actual content. Other quality of the signature is that by changing some text, we cannot explicitly, we cannot change this text in such a way that we can generate signature of our choice. Even if single byte is changed in this text file, the signature will change entirely. Signature will change entirely. Okay, I'm going to show you this right away here. So this is one image that we are doing right now. Let's create its signature. Okay, let's create the signature of this file, the image file that we have just drawn. Okay, and right now we are using one algorithm called MD5. Okay, so I'm going to compute the signature of this file. You see that? The signature of this file is this. We are using MD5 here, and using MD5, the signature is coming out to be this. All right. Now, no matter which system I'm using, the signature of this file is going to be this. Okay. As long as the file is same, the signature will remain the same. Okay. Till now, the signatures are same, but the moment I put one more dot somewhere, like here, now the signatures will change. Okay, now the signatures have entirely changed. I just put a dot. Okay, you see that? The signature has entirely changed. This is called this is called cryptographic signature. This is called cryptographic signature. I think this is 16. I think this is, how many characters are there? One. I'll just check it. Okay, it's 32-bit. All right, it's a 32 byte signature. So what I demonstrated to you that MD5 is one just such algorithm that creates signature, and we can create signature of even such text like Sandeep, right? This is also a text, and I can pipe this data to MD5, and the size of the signature for this string is also of the same size. Okay, so this is fixed size output. Do I make sense, or did I confuse you? All right. What does the content after MD5 come from? After MD5, okay, this line is the location of my image. I was dragging and dropping this image, which I was drawing. So this is the location of that image. Okay, so either we could pass the input to MD5 using standard input by piping, or we could pass the argument to this as a file. Okay, so let's take another file. Let's take this Scala SDK. Okay, I'm saying MD5 Scala SDK. There also the MD5 checksum is this. You see that? The MD5 checksum of this file is this. So what we learned is no matter what's the size of the file, if you take a look at the size of the file, it is okay. It is huge. Okay, let me put H here. Okay, it's 16 MB, and for the 16 MB file, the signature was also the same. Okay, so signature is basically of the fixed size. There are many algorithms which are able to provide this cryptographic signature, so that so that so these algorithms are really interesting. You can create the signature of something, but you can never reproduce the actual content from the signature. And it's used in many systems than you can imagine. These signatures are integral part of the computing. Signatures are used in storing your password. So instead of saving your password, system should always store the checksum or signature of your password instead of the actual password. And the way it compares is when you enter a password, it will compute the signature and compare the signature instead of actual password, because system does not keep this. System should never keep your passwords. System should only always keep the signature. Okay, so Pawan's question is, MD5 reads the whole file to create hash or just random content? What do you say? Anybody? So had it been doing the random, what would happen is every time we run this MD5 checksum, it'll give us the same result. Also, had it been just say taking the first few length of the file, what would happen is people could modify their actual data and produce the signature. Okay, nobody can create a file of their own choice with their own choice of signature. I can never modify this file such that its signature is same as some other file. This I cannot do it by my choice. Okay, it's not possible to do change the file and expect the same signature. Question from Pavan is, what will happen if the file is very big? Good question. In that case, also it has to take the whole file and compute the signature. And of course, there could be other items that have the same signature. Theoretically, yes. There could be other items that could happen, that could definitely happen because signature of the is of the fixed size, and there are so many other data sets in the world, right? Therefore, there could be other data sets that have the same signature, but it's not possible to create that. It's not possible to, given a signature, it's not possible to figure out which all content could lead to this signature. Yes, yes, Pawan, it definitely takes a long time to compute the checksum of huge files. Okay, and that's why the systems which are supposed to handle huge files, they provide you methods to compute signature by themselves. For example, Hadoop's HDFS, it provides you the way to quickly give you the signature, because it, at the time of saving itself, it computes the signature. All right, is everybody okay with this? Yes, that's possible, Kamal, what you're suggesting, but the possibility is really, really low. All right. Question from Noor. That could be a stats question to know the probability of having same hash. It's actually very, very low, and that's the idea around MD5. And MD5 got cracked once, predictably. Before this MD5, there used to be DES, right? And DES got cracked long back, so they created MD5. And now there was a weakness in MD5, so now people use SHA-1. Okay, SHA-1 is also used very frequently. It's the same algorithm as, okay, same algorithm as, it's similar, not same. It's basically more robust. So this is SHA-1. Okay, so we can compute the checksum using another algorithm called SHA-1, and that's the one that's being used right now instead of MD5. Okay. Yes, that's right, Noor. We might need to have a little bigger checksum. So SHA-sum is little bigger than the MD5. Okay, good point. Very good point. So if is everybody clear about MD5? Okay. In sorry. Okay. So in Python, this is how you can use the MD5. I'll show you. So let me do that for, say, Sandeep. And okay, it's asking me to do it Unicode. Unicode object must be encoded. Okay, how do you encode it? All right, I'll see that later. I think I'll have to encode it into binary array and then it'll work. Okay, never mind. So moving ahead. Okay, so basically this is how we need to this is how we create the just give me a second, I'll try this one. Np dot int 64. I'm just trying to compute the, okay, you see that. All right, it has created the MD5 checksum of this number. It's in the binary format. We can convert this to a string. Okay, and that'll be okay. All right, so we have a function called hashlib. In hashlib, we have a function called MD5, which produces the signature of anything that is passed to as argument. Okay. Yes, it is not auto-completing. All right. So digest is the function which produces the checksum or signature. So this function is also called. So there are three functions like SHA1. Earlier there used to be DES, but that's we are not include. There were some other ones also. We are not including those. And coming back to the point. So these are the various algorithms. Now, what was I talking about? Okay. So these are called either checksum, signature, hash code, or simply hash functions. Okay. And sometimes we call it cryptographic hash. Okay. So these are the various names for the same thing. Okay, so checksum, signature, hash functions, or cryptographic hash. All right, so what is it that we are trying to do is we are trying to create the row number we are trying to create data set based on based on the row identifier. There could be many record identifier. We just need to convert that record identifier and code that into something, and then uh, uh, decide whether to pick or not. Okay, although here we are kind of using really huge thing as Pawan was suggesting that MD5 could take a long time, and if the file is big it could be really long. Similarly here it's going to be really costly affair, so there could be other alternative techniques as well. So all we are doing is, so what does it mean by digest? Digest is a function that produces the output, produces the hash. Okay. Okay, so sometimes we also call it digest, the same hash functions value. Okay, now coming back to that, yeah. So all this function does is it returns true or false. It returns true or false given an identifier. And how does it do that? First, it converts that identifier into a hash value, and then it picks the last value in this. It basically picks the last value in this. I'll show you. So here it's going to pick the last value. Okay, so the value here, it is 45. Okay, so from this huge digest, it's just picking the last value, and then it's saying that if this value is lesser than 256 into test ratio. Test ratio is somewhere between 0 to 1, while the value of individual character, individual this letter is going to be somewhere between 0 to 256. Okay, because it's a single character could vary the value of this each digit. The ASCII value of each digit could vary from 0 to 256. Okay, so it's saying that if the so 256 multiplied by test ratio will be some portion of 256. Okay, if this is 0.2, then 256 into 0.2 will be a small number, right? So if this last digit is lesser than that, then pick it, because last digit could vary from 0 to 256. Okay, the last digit of this could vary from 0 to 256, and that's why we are saying, okay, how should I explain this one? So the last digit of the number could vary from 0 to 256. Okay, correct? So the last character, actually the ASCII value of that character is going to be somewhere between 0 to 256, and here we are saying um, that value should be lesser than 256 multiplied by 256 multiplied by the ratio. And how much is the ratio? Ratio is 25%, 0.2, right? So this is 20%. So we are saying that if the value that with that character that we are picking up, if that value is less than this, only then pick it. Okay, therefore it's going to pick only 1/4 of the total numbers. Okay, 1/4 of the total numbers. Okay, so this condition is going to return true only for 20% of the total records if the test ratio is 0.2. Okay, and that's going to be not random but based on some skewed conversion. Okay, some skewed conversion. So basically test set check returns true or false in a way that if it is called on the whole data set, you will get 20% of the total records. Okay, so instead of using the permutation, random permutation, we are using this identifier. We are using this identifier to pick up the the records or ignore the records. All right. So it's just one of the criteria. It's just one strategy. There could be hundreds or thousands of ways of picking up records from a data set based on an identifier. Okay, there are other ways of we can sum up all the digits, divide them by a certain value, and then we pick the results. Okay, so that also can be done, and these are standard techniques for partitioning the data. All right, so what we are trying to do is we are trying to figure out a way of randomly picking elements, randomly picking records based on certain identifier. So here what we're trying to do is we are saying, so let's start from here. So this is our new function called split test train data by ID. This is our data, this is our ratio, this is the column on which we are going to on the basis of which we are going to identify the records, and this is the hash function. Okay, this is our hash function. We could use newer functions. Here we are saying that if this is not provided, this value is not provided, we will assume this to be MD5. So we can call this function with only 3 arguments. Okay, this is the default value for this argument. So we are saying here we are starting with identifying, just picking up the ID. So we are saying data and accessing ID column, we are getting this value. Then on these IDs, we are applying, okay, sorry, let me say it again. For this data, for this column, we are picking all of the values. We're picking all of the values, you see that? Okay, so for the whole column we have picked up. Okay, now on this, we are calling our function. On every record of IDs, on every row of this column, we are going to apply a function. And what function is that? This function returns true or false. True means we will be including that record. If false, we will be ignoring that record. Okay, what is the type of the ID? It will depend on which column are we picking. Okay, and here the good news about the checksum is that they can compute the checksum of string, numbers, or any binary data. Okay, that's the reason probably why MD5 is being used. A question from Tanmay: should this be in code? No, it's actually this is basically a module which we have imported. So we are passing the function as argument. Okay, we're passing the function as argument. All right, so we can pass the function as argument to another function. Okay, so here we are saying that for every record, call test set check. So we are saying IDs dot apply, and we are passing this function, and then it's applying this function again and again on every record. On every record, this function is being applied, and this is being called. Okay, so we are also passing the hash function here. Okay, and that's it. So once we get this test set, now based on this, we could either say not of this, or we could say normal. Not of this mean this will be a huge array of trues and false. Okay, it'll be a column, or it'll be basically what do you call it, series. It will be a series of true and false. Okay, so we are saying that return this, not of this, and return actual of this. Okay, so it'll pick up those records for which these values are true, false here, and records for which these values are true. Okay, so this is basically a list of flags containing true and false Boolean values, and not of this means opposite of this. We'll toggle the values of all of this. And you remember, if we pass the series containing true and false, it'll basically skip the records where the value of the series is false. Okay, so this is the way we were picking the rows, right? This is how we picked up the rows earlier while we discussed pandas, correct? So based on these flags, we have now splitted this data. That's right, Tanmay. Okay, did I make sense here? So here, more than the function, the individual concepts are very important, because function, we already have similar functions available as part of some packages. Okay. A question from Noor: this is fine, but test set check is not clear. Okay, this is not clear. So here what we are doing is we are first computing the checksum. It will generate a fixed size signature, some random signature. Just that it's not so random because it is dependent on identifier. If the identifier is same, the hash function will always return the same value. And when we say digest, it is the function which returns the value in the binary format. I think it returns in a character format. Okay. Now here we are saying -1. -1 means give me the last character of it. And we are saying that if this value is lesser than this, the max value of this is 256, right? And we are saying if this value is lesser than this, okay, which is say 1/5 of the total size, that means that this will only return true. This will only return true in 1/5 of the cases. Okay, because its value could go from 0 to 256, and we are saying that this should be lesser than 256 by 5. That means that means that that means that this would return true only in case of 20% of the records. right? Because this value is 20% of the total. Test ratio is 20%, right? A question from Tanmay. Performance-wise, we have to parse data twice. Okay, kind of yes. Here, basically, this is the most intensive function here. We are applying this function on every row of this series, this column. Okay, and then we have to pick up these records. So yes, it's kind of twice. Okay, a question from Noor is that how will it get the same set of records? So if same as in if a particular record went into training, it will always go into training. It won't switch to test. Okay, just because we have added new records. That's what we are trying to avoid. We're trying to avoid the fact that in case new records are added to our data set, the record which was marked as the training data set should not go in the test data set. That will never happen because the identifier, whatever identifier we choose, should remain same. Okay, should remain same. Now question is, what identifier, what column should we choose as identifier that would remain same over a period of time? Is that your question? In case of housing, the latitude longitude combination is going to remain the same. Okay, therefore the identifier will remain the same for those records which were marked as training earlier, and hence the records will not switch, while new records will be added to both. Do I make sense, Noor? Yes, it's not incremental. It works on whole data set. Just that since we have identifier for every record, the records with the same identifier will always go in the same bucket. Okay, they will not switch their party. Okay, good question. All right, so was I able to answer, Tanmay? Yes, it is basically a little bit going to be big performance hog. Okay, but we can speed up this process by having low overhead hashing function, because MD5 function is little big overhead. There are far more cheaper alternatives to it. Okay, all right, so the lock is basically when you want to access the rows, then you use lock. If you want to if you remember our discussion from pandas, that if we have I'll show you. So let me show you with the housing example. Okay, I'm creating a smaller data. Okay, I'm calling it S5 and saying housing dot head. Okay, so S5 is, if you take a look at it, S5 is basically 5 records. Okay, so if I say give me say true, give me true, false, 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 false. So what will it do? It'll give me the first record, right? It has given me the first record, right? And if I say iLock, then it would expect me to provide the record number, right? It'll expect me to provide, say, the indexes of the records that I would like to access. So you can see that it has given me first and second. Now it makes sense to you? So log gives us the rows for which the flags are true. Okay? And the flags are passed as an array in the argument. Bintao, did I make sense to you? Okay, so Tanmay, yes, that you are right. So you're correct on the track. All right, so great. Yes. Okay, you want me to explain, Noor, this part? Sure, sure. Actually, this is a little harder part, so I'll describe this in more details. Kamal, are you with me? Is everybody with me, or okay? So yes, so those who are interested in learning this, they can stay back if you okay. And okay, so we will continue the next session from here. Okay, we have already covered most of these parts, so we're going to, this is the hardest part to go through. Rest of the things are going to be far more simpler. All right. Yes, so we were talking about this function, right? So my question to you is, okay, let me take this out, right? Okay, where did it go? Okay, I think, let me break it down. Okay, so a question to you is, what does it return? What does it return? It returns, it returns true or false, correct? We are comparing this, sorry, we're comparing this part with this part, right? And what is this part on the left hand side? The left hand side is the left hand side is um, first we compute hash, first we compute hash, right? Let's take a look of, say, let me just show you what it means by this portion, right? So you can take a look here. So we are saying, first of all, we are saying now we're converting this number, into a 64-bit number. Okay, so it's nothing but same number, but data type is different. Then we are computing the hash of this number. Okay, we are computing hash of this number. Okay, so how does it look like? It looks like a binary object. Now out of that binary object, we only want the digest portion of it. Okay, digest portion of it. You see that? The digest portion of it. Now we want the last character of this one. Last character of this one. Okay, as a matter of fact, here we could have picked up even the first character of it. Okay, that could have been giving us the same result. Okay, so we could also say for I in range. All right, so let's call it X. I'm going to just show you how it varies, and I'm going to say X and I. Okay. Okay, so you can see that the when we access the individual parts of this digest, they were this kind of numbers, right? They're varying from one point to another. Okay, if we change this identifier to something else, there'll be this kind of number. So what's the biggest number you have encountered so far? 256, 251, and the smallest number is 92, and so on, right? So you can see that the outcome, the any character of this digest is varying. This side is going from where to where? This side is varying from 0 to 256. Okay, the left hand side could vary from 0 to 256, and the right hand side's value is how much? 256 into say 0.2. Okay, which is around how much? 51. Correct? So if the left hand side is varying from 0 to 56 and right hand side is 51, so how many values, how many times this will be true? How many times this condition will be true? Only 20% of the time, right? So this function will return true 20% of the time and false rest of the time, right? If the test ratio is 20%. So we computed the first converted into 64-bit, then computed hash, extracted digest, picked the last character. Instead of last character, we could have also picked up the 0th character and or maybe any character. Okay. So that character is going to vary from 0 to 256 and so on. All right, Noor, did I make sense to you? All right, great. So yes, this was a little harder part. So because there were many unknown terms, and since it's a code which is not really comfortable to the eyes, and that's why. Okay, so this way we basically splitted data based on an identifier. This way we have defined a function which can split the data based on an identifier. All right, so we will continue from here. Do not worry about the pace. This is basically the time where we get comfortable with the ideas, and initially it would take more time to get to many things instead of just mugging up the algorithms available. Okay, this is the stable way of learning, and this would help all of us gain a good command over the ideas behind machine learning. The functions could change, algorithms could change, but these ideas, this theory, or this strategy would remain same. Okay, whether we are going for neural net, whether we are going for any kind of things, these ideas will be useful. Okay, a question from Kamal: since the creation of MD5 is random, it might be that the test set does not exactly have 20% data. Yes, there could be one or two records above or below. Good point, Kamal. All right, it will never be identical. If we are trying to do permutation and if you're trying to pick random numbers, it'll never be exactly 20%, and which is okay. All right, so thank you everyone, and yes. All right, I look forward to see you in the next session. The questions will be we'll be adding more questions to the CloudxLab LMS, and we will inform you as soon as we are done with adding questions. All right. I hope all of you have finished the assignments of Python. The last project, how many of you have done? Okay, so please email your results to me. That'll be great. All right. So thank you, everyone. I look forward to see you in the next session. Bye-bye. Have a good day.